Welcome to Chapter 10. In this chapter, we're discussing transaction management and concurrency control. Concurrent execution of user programs is essential for good database management system performance. Disk access is frequent and it's very slow. And we want to keep the CPU busy. A transaction is the database management system's abstract view of a user program as a series of reads and writes of database objects. So, a database may have many simultaneous users, and a simultaneous users implies that simultaneous transactions will occur, and that implies that there'll be simultaneous database access. And things can go wrong. Concurrent actions can conflict with each other. Programs may crash. The operating system may crash. The disk may crash. And if we're not careful, the company loses customer data or customer orders. It gets sued because of this. Potentially goes bankrupt if it happens often. So in this chapter, we're going to talk about database transactions and their properties, what concurrent control is, and what role it plays in maintaining the database's integrity, and what locking methods are and how they work. So users submit transactions, and we can think of each transaction as executing by itself. The concurrency is achieved by the database management system, which interleaves actions of the various transactions. Some of the issues are conflicts between the interleaving transactions and crashes. So a transaction is a logical unit of work that consists of a select statement, series of update statements, insert statements, or a combination of these three kinds of statements. The transaction manager So the goal of a transaction manager, which is part of the database management system, is to start transactions, locate and start the right program, and ensure timely and fair scheduling for that transaction, log the activities, especially start and stop, writes, commits, and aborts. It detects and avoids conflicts, and it takes recovery actions. And the goal is to have a consistent database state. All the data integrity constraints are satisfied, and we begin with a database in a known consistent state, and we end with a database in a known consistent state. So, a transaction is formed by two or more database requests. A database request is the equivalent of a single SQL statement in an application, program, or transaction. It consists of a single SQL statement or a collection of related SQL statements. So again, a transaction is a unit of work of program execution that accesses and updates various data items. The classic example given in the literature for database transactions is transferring $50 from bank account A to bank account B. So the steps are: we read A, and then we subtract $50 from A. Then we write A. Then we read B, and we add $50 to B, and then we write B. So there's two main issues to deal with here. We've got 6 steps there, and failures of various kinds, such as hardware failures and system crashes, other concurrent execution of multiple transactions, might interfere with some of this activity. So what happens if we subtract $50 from our customer A's account and write it, and then we're in the process of adding $50 to customer B's account, but it doesn't happen because of one of those failures? Well, then customer B is mad because he didn't get his money, and customer A is mad because $50 was taken from their account. So if we establish a transaction as a unit of work that incorporates all 6 steps as one unit of work, then it either all succeeds or it all fails. So if we read A and write A and read B and then it fails before we update B and write B, then the whole thing is rolled back. What we wrote for transaction A is rolled back. So improper or incomplete transactions have a devastating effect on the database integrity. So we can define enforceable constraints in the idea of a transaction that'll help us deal with those. So a transaction is a sequence of statements that either all succeed or all fail. Transactions have what are known as the ACID properties: atomicity, consistency, independence, and durability. Atomicity means either all actions are carried out or none are. Consistency means if each transaction is consistent and the database is initially consistent, then it is left in a consistent state. Isolation means that transactions are isolated or protected from the effects of other scheduled transactions. And durability is if a transaction completes successfully, then its effects persist. And we'll look at serializability in more detail in a few slides. So transactions go through several states. They're active, that's the initial state. The transaction stays in this state while it's executing. Partially committed. After the final statement has been executed, the transaction is considered to be partially committed. Failed. That's after the discovery that normal execution can no longer proceed. Aborted. After the transaction has been rolled back and the database restored to its prior state, in other words, to the start of the transaction. There's 2 options after a transaction has been aborted. We can restart the transaction, and that can be done only if there's no internal logic error, or kill the transaction. And then finally, we have the state of a committed transaction, and that's after the successful completion of all steps. A commit, as an application program is executing, it is in a transaction. Programs can execute a commit, and these are SQL commands to finish the transaction successfully. The next SQL statement will automatically start a new transaction. There's also a rollback. So if the application gets to a place where it can't complete the transaction successfully, it can execute a rollback. This causes the system to abort the transaction. The database returns, once it does the abort, the database returns to the state without any of the previous changes made by activity of the transaction. So if there was previous activity that was successful, but the latter part of the transaction failed, everything is rolled back. And here we see the states. It can be active and it successfully completes. And then if it successfully completes, it's in a partially committed state. So the application is finished, but then what happens if the database management system has an error, or the operating system has an error, or there's a hardware error? Well, then we go from partially committed to failed. If none of those things happen, we go from partially committed to fully committed, and the database is permanently updated. Once we're in the failed state, we then go to the aborted state where we roll back the earlier effects of parts of our transaction. Okay. So here's an example of what a transaction looks like in Oracle. Now, as I had mentioned, many times SQL is the same between the major vendors. This is one of the cases where it's not. They all have unique ways of handling transactions. And we'll see Microsoft SQL Server's approach to it in just a few moments. But this is the way Oracle does it. And so we can see they begin a transaction. The transaction is they're going to do some inserts. They can also have multiple updates after that, as you can see in this pseudocode, more updates here. Then if everything went okay, commit, else roll back. So if the system crashes, the transaction will be committed or aborted depending on if it was finished. If the transaction was finished and ready to go, then it will be committed. Otherwise, it'll be aborted if the system crashes before it reaches that state. So how does the database management system get this protection and create transactions? Well, the way it does it is you have applications that, an application that uses the database, and it will be writing its activities. In other words, I'm going to add $50 to account A, I'm going to subtract $50 from account B, commit. It'll be writing those to what's known as a transaction log. So if you see a commit in the transaction log, then you know, okay, this is a complete transaction. Then the database management system will read the transaction log, and it'll be doing this in the background. And when it reaches a fully committed transaction, it will then update the database. And if the database was successfully updated, then it'll place an updated in the transaction log. Once the database is updated, then we have a fully committed transaction. So the transaction log keeps track of all the transactions that update the database. The database management system uses the information stored in a log for recovery requirements triggered by a rollback, a program's abnormal termination, and a system failure. So we not only do successful transactions here, but what happens if we see a transaction and it never has a commit? Well, then we know that we've got a problem, so then we just mark, okay, aborted, and we leave it there. We do not take the information out of the transaction log and put it into the database. It's there as a record in the transaction log, but it never contaminates our database. So let's take a look at a transaction in Microsoft SQL Server. Let's take a look at how transactions work in practice. This is Microsoft SQL Server. It's one of the most powerful databases on the market. And I've loaded our university database into SQL Server. And you can see here that I've selected all of the records from the instructor table. And note particularly that we have one instructor named Brown already in our database. Now, we have an ID for him, and the ID is the primary key for the instructor table. And again, a primary key prevents you from adding another record that has the same ID. So Brown's ID is 25566. So if we tried to add another ID with that same value, a SQL Server would reject that attempt. It'll reject that insert. Now, we've been saying in this lecture that a transaction is where we're going to put several database modification statements into what is known as a transaction, and that transaction will execute as a block. So in other words, it will all completely execute, or none of it will execute and won't be written to the database. It will not update our database. So the stage is set here. We know we've got Brown, and we're going to have a transaction where we try and put Brown in again, and hopefully it'll reject and roll back the entire transaction. So here's our transaction. And this is written to do programming-like actions against your database that give you a lot more capacity or capability than you would have with just plain SQL. So this is how we set up a transaction in Microsoft. We use Transact SQL. So you can see up top we set our transactions on. Then we're going to try our transaction. We use a begin-end block for that. And we're going to insert two records, one with my name and a... Okay, so this is how it works in Microsoft SQL Server, and in general, the other database vendors follow the same pattern, if not with slightly different syntax. So, concurrent instructions are multiple transactions that are allowed to run concurrently in the system. The advantages of doing this are increased processor and disk utilization, and this leads to better transaction throughput. For example, one transaction can be using the CPU while another is reading from or writing to the disk. It reduces the average response time for transactions. Short transactions don't need to wait behind long ones. They can run in parallel. Some of the concurrency control schemes are mechanisms to achieve isolation, and that is to control the interaction among the concurrent transactions in order to prevent them from destroying the consistency of the database. And this coordination of simultaneous transactions executing in a multi-user database system is called concurrency control. And again, its objective is to make sure that we have serializable transactions. So there's some famous anomalies that can happen when we do not properly manage the concurrent interaction of transactions. One is the lost updates. Consider we have two tasks, T and T prime, that both modify the same data. T and T prime both commit, and the final state shows only the effects of transaction T, which overwrote the effects of transaction T prime. Another is uncommitted data, and uncommitted data occurs when two transactions are executed concurrently. The first transaction is rolled back after the second transaction has already accessed the uncommitted data. Then we have inconsistent retrievals or dirty data, and one task, T, reads data written by T prime while T prime is running. Then T prime aborts, so the data was rolled back, its data was not appropriate. We have others like read-write, conflict, and unrepeatable reads. One task can overwrite the work of another. One task can change the value of data read by another. So these are some of the famous anomalies. And the way we go about resolving this problem was actually developed by someone at Microsoft, Jim Gray, who was awarded the Turing Award for his work. And it involves the creation of schedules. And then we have a serializable schedule, and if we can get two different transactions into a serializable schedule, then we can run them concurrently. Otherwise, we have to run them one after the other. So a schedule is a sequence of instructions that specifies the chronological order in which instructions of concurrent transactions are executed. A schedule for a set of transactions must consist of all instructions for those transactions. It must preserve the order in which the instructions appear in each individual transaction. A transaction that successfully completes its execution will have a commit instruction as the last statement. By default, transactions are assumed to execute commit instructions as its last step. A transaction that fails to successfully complete its transaction will have an abort instruction as its last statement. So, conflict serializability, we create a serializable schedule. So if a schedule S can be transformed into a schedule S prime by a series of swaps of non-conflicting instructions, we say that S and S prime are conflict equivalent. We say that a schedule S is conflict serializable if it is conflict equivalent to a serializable schedule. So, remember, serial execution of a set of transactions will preserve the database consistency. Transaction 1 runs to completion, and then transaction 2 starts, and it runs to completion. They're not interfering with each other because they're not running at the same time. If we can swap instructions without affecting the result of any instructions, then we can, in effect, make what we can run two different transactions, T1 and T2, at the same time. So, for instructions operating on the same item, in other words, transaction A and transaction B are both operating on the instructor table, we can only swap reads. So if they're both reading the instructor table, then we can swap them and try to get what appears to be a serializable schedule. If they're working on different items, let's say transaction A is working on the student table and transaction B is working on the instructor table, we can swap instructions on different items without affecting the result of any instruction. So let's take a look at a couple of schedules. And again, we'll go back to our two transactions. We're going to have a transaction that transfers $50 from account A to account B, and then another transaction that transfers 10% of the balance from A to B. So we see a serial schedule here where the vertical axis is time, and we can see that transaction 1 is completely done. We've taken $50 from A and given it to B. Then, after that's done, we calculate a 10% bonus on each account. Well, we transfer 10% of account A to account B. And that is done in the proper order. We've taken $50 out, then we calculate the 10%. So this is a serial schedule, and it doesn't have any problems. But we're not running transaction 1 and transaction 2 at the same time. Pardon me. So we lack that concurrency that we talked about earlier in this lecture. So what happens if we do something like this? We run transaction 1, and then we start running transaction 2 before transaction 1 is completed. Well, if we can take this, and this is what the Query Optimizer will be doing. It's going to be looking to see, of all the transactions it has backed up, which ones can it serialize. So can it take two transactions like this and look at the statements and say, okay, I will block out this subset of T1, this subset of T2, and when T1, when I'm waiting for the result to come back from the disk for T1, then I will start working on T2. So here the question is, if this is something that would enable the Query Optimizer to run these transactions concurrently, is it equivalent to a serial schedule like we saw in Schedule 1? Well, in this case it is, because we look at, we've written A in the first block here, then the second block, pardon me, the second block we're working on A again, but then transaction 1 is working on B. So this part of transaction 2 is working on A, this one's working on B. They're working on different items, so we can swap these things because they are working on different items. And then when we do that, we get the equivalent of this. We move the B part up here and the A part down there. We have, in effect, a serializable schedule. So this one is conflict serializable. On the other hand, let's look at this one. So we're reading A here, and then we're going to write A, and then we're going to read B. So we can't swap these two because they're both working on the same item, A, and one of them is doing a write, so we can't swap them. Likewise, if we look down here, we've got, we're reading A, and then we're writing A down here. So again, because we're doing a write to A, we can't swap them. So we cannot swap these blocks of instructions around to achieve the equivalent of a serial schedule. And because of that, the compiler will then say, I cannot run T1 and T2 concurrently. I'll go look for another partner I might run with T1. So it does that all along while it's waiting to execute these things to see which pairings it can make. So locking is how we let every other application know that we're going to be working with this type, with this database part. So it can be the entire database, it can be a table in the database, it can be a page, which is an operating system block of space, it can be a page within a table, or it can be an individual row that we're locking. The lock manager is responsible for assigning and policing the locks used by the transactions. So the granularity of the locks can be at various levels. It can be database level, table level, page level. And as I mentioned, it's a page is a directly accessible section of a disk. It can be at the row level or at the field level. So here we see a database level lock. This is the worst kind of lock because it prevents you another transaction from working on the database, even if it's working on a different part of the database. So here transaction 1 is working on table A. It puts in place a database lock and gets it, and then along comes transaction 2 and it wants to update table B, a completely different table. Well, because the database is locked, transaction B has to wait 4 time periods before it can actually begin, whereas it should have been able to begin right at time period 1. A little bit better is a table level lock. And here, 2 different transactions that work on different tables can run concurrently, but if 2 transactions are working on the same table, then we run into the same problem. In this case, transaction 1 is working with table A, and it's going to update row 5. Transaction 2 is likewise working on table A, and it intends on updating row 30. So with a table level lock, then transaction 2 has to wait 4 time periods before it can begin when it should have been able to begin in time period 1. Because again, it's working on something different. It's working on a different object. Now here's a page level lock, and this is a little bit better than a table lock. So we have transaction 1 and transaction 2. Here they're both trying to update page 1. So transaction 1 has a request for a lock on page 1 because it's going to update row 1. Transaction 2 needs to lock pages 1 and 2 because it's going to update record 2 and record 5. Well, it's got to wait because transaction 1 has a lock on page 1 as a result of the need to update row 1. So the most granular level, well, one of the more granular levels that we can get to is the row level. So here we have transaction 1, it's updating row 1, and it makes a lock request there. A transaction 2 comes along and it requests a lock on row 2, and it can get that because no one's locking row 2. And then they both finish, they're completed well ahead of what they would have been had they been waiting on page locks, table locks, or database locks. So you can see there's a real advantage to getting row-level locking in a database. And that was the goal of these major database vendors to get to that level of locking. When Microsoft first got SQL Server, they bought it from Sybase. It did not have row-level locking, and we hired a powerful team of database experts to go and come up with a system for doing row-level locking in SQL Server. So an exclusive lock is reserved for the transaction, and it gets only that transaction gets access to that locked object. A shared lock occurs when concurrent transactions are granted read access on the same common block. So you'll do that so you don't get this case where you read something, another application comes in and updates it, you make a change, and then you want to go in and update it, but then you'd be overwriting what the other transaction did. And so the way you handle that is you put a shared lock on. Means other transactions can read it, but no one can update it. Now, there are problems using locks, and the database management engines and the query optimizers are getting better and better at preventing these and helping you unwind them. But you will get in the case occasionally where you have a deadlock, where transaction 1 has object A locked and needs to get a lock on object B, and transaction 2 has the opposite. It has object B locked and it needs to get a lock on object A, and so they're both waiting for each other, but they'll never get it until the other finishes and releases the resource they need. So there are still problems, although not as common as they used to be. So two-phase locking, that's how transactions acquire and relinquish locks. Those phases are the growing phase. The transaction acquires all the required locks without unlocking any data. And then we have the shrinking phase, where the transaction releases all locks and it cannot obtain a new lock. So some of the governing rules: two transactions cannot have conflicting locks. A no lock operation can precede or come before, let me say it that way, a lock operation in the same transaction. And no data are affected until the locks are obtained. And here we see a two-phase locking protocol over 8 time periods. You acquire a lock, you're at a locked point, you do your operations, then you release a lock, and you end your transaction. So you have the growing phase where you're acquiring the locks you need. The locked phase, I've got all the locks I need, I must quickly do my business and update. Then you start releasing the locks as you don't need them. So we've talked about the deadly embrace, where two transactions will wait indefinitely for each other to unlock data. Some of the control techniques are deadlock prevention methods, deadlock detection methods, and deadlock avoidance. And different database environments will have different approaches to this, and that's what gives them their proprietary advantages. Timestamping is one approach. It uses a global timestamp in each transaction, produces explicit order in which the transactions are submitted to the database management system. So then after we've got these transactions in our transaction log, what happens if we have a database failure and we have to do a database recovery? Well, database recovery restores the database from a given backup for a previously consistent state. So it takes an old backup of the database and it writes it in, overwrites what's in the current database now. But we still maintain the transaction log. Then the database management system will read through the transaction log to see if there's any completed transactions in the transaction log that it can apply to the database, and so we don't lose all of the work that we had done. And again, we have this whole idea. You have a transaction as a series of inserts, updates, and reads, and so on. If it's atomic and completed, then we commit it. If it's atomic and we don't see a commit, then everything is aborted. We don't write any of the transaction parts into our database. And that's known as rolling back the changes. Essentially, you're just not writing them in the first place. You're writing them to the transaction log, but you put a mark there, aborted, so that'll prevent it from looking and consider it in the future, and you don't write it from the transaction log to your permanent database files. Okay, so this concludes Chapter 10 in our database textbook. Unique ID, so that one should go in just fine. Then the next one is we're going to try and insert Brown again, and that'll reject. Now, if we've done our transaction correctly, even though the insert to instructor for George was successful, it will be rolled back when the insert for Brown is unsuccessful. And you can see that if we do have a problem, we have a catch block where we catch the error and we print out the error information, and that'll tell us if things are going okay. So let's try and execute this particular transaction and see what happens. So at the bottom you can see the result of the attempt, and it gives us an error message, and the error message is violation of primary key constraint. And of course we knew that was going to be a problem when we set this up. We wanted it to be a problem. And now let's see if George is in that database. So we'll come back, we'll re-execute this query. You'll notice that Brown is in there, of course, but 255667 would have been immediately after Brown, and that one is not there because it was rolled back. In other words, even though it was a successful insert, after it was successfully inserted, Brown failed, and they were part of the same transaction, and therefore both of those inserts were not inserted. One was rolled back and the other, of course, was a failure.